We're working on calculating the cache size. So you will be given descriptive problem set, including the cache size of the block. For us, it's always 32-bit address. And this part, as a byte addressing or word addressing, it's going to be different ones. So we haven't talked about word addressing yet. We did actually. The first problem we did, that was the word addressing. But that's something you need to really pay attention to. So to calculate the size of the cache, what we need to do, first we need to find out total number of bits for index or set. How? 2 to the n equals to cache size over block size. So cache size is given as a 16 kilobyte, and then block size as the 4-word block. And there are different units, so you need to unify the unit, either 2 bytes or 2 words, right? Then you can cancel that out. We have a 2 to the power of 10, and n value from there equals to 10. That is the total number of bits. And then we need to calculate the text size. Text size equals to 32. That's the total number of bits for memory address, minus n plus m plus 2, and we have there. Now how to find the m? The block size in a word, and then 2 to the power of m. This m, we need to plug it in here. And for here, what's the block size? 4-word block, so the n value is going to be 2. M plus 2 is going to give us the total offset. So the text size is 32 minus 10 plus 2, 18. And then valid bit is always 1. Therefore, this is the format of our memory address. Offset is 4, 2 plus 2. Index, set bit is n equals to 10, total number of 10, and then 32 minus 14, which is 18. So we'll look at this diagram. We need the 4 offset. That's what we did. Okay, so let's work on the larger block size. This time, say to what block number does byte address 1200 is going to map if it uses 64 blocks and block size of 16 byte. Okay, the first thing we need to do, 2 to the n equals to cache over block size. Block size of 16 byte. Okay, we can plug it in here. Cache size. Wait a minute, there's no cache size. Actual problem is not asking us to find the cache size, but I want to find out the cache size. However, the cache size is not given. How do you know the value of n? Anybody? How we can figure it out, the value of n? Because cache size is not given. Yeah, total number of blocks is given. Total number of blocks is given. So we have 64 blocks of the cache. We want to name those 64 blocks using binary number. How many bits do we need to have to name all those 64 blocks? How many bits? 2, 0, 1, 2, 1, 2, 2, 2, 4, 8, 16. Yeah, I was going to say. So we have 64 blocks, n equals to 6 now. Now we need to calculate the text size. Calculate the text size, we need to have a 32 minus n plus m plus 2. And the block size is given as a 16 byte. 16 byte is 4 word. 4 word is 2 to the power of 2 words. Therefore, m equals to 2. Text size is now 32 minus 16 plus 2 is 22. Total size is 2 to the power of n, which is 6. Block size 16 times 8. Why? Because it's a byte, 16 byte, 16 times 8. Plus text size is 22. Valid bit is 1. 2 to the power of 6 times 151 bits. We calculate the size of the cache. Now we need to figure it out. The byte address 1200, where is it? That's what we need to do. Oh, this should be 6, 8, 10, 22. You're right, right. It's a typo. This should be 6. So it was typo. So now we have 1200, the byte address 1200, and we have the 16 bytes of the block size. So I'm going to divide 1200, that's the byte addressing, divide by 16, why 16? Because that's the block size, so that I can go to that block. First thing we want to do is to which block is in this 1200, right? And each block is 16 byte, and this is the byte address. That's why we need to divide 1200 divided by 16. This symbol is rounding down. If this is the decimal point, we're going to round down. So the 75. But we only have 64 blocks. That's why we have 75 modulo 64, because it's 64. So actually 11, that's the block number. The byte address 1200 is located in block number 11. That's what it is. So now we have this guy. So block is going to go from 0 to 64. And each block we have a 16 bytes. So this is byte address 0, byte address 1, 2, 3. And this is going to be byte address 16. And all the way down to byte address 1008. And then byte address 1023. That's the end of it. Then 1020 byte address 1024 is going to be here, and so on. So byte address 1200 is in this location, which is the block number 11. Questions. 75 mod, we have 64. So when we have something like this, you're going to divide 75, 64, and 1, 64, 11, that's the remainder. So when you calculate the mod, it's telling us the remainder when you divide this number by this number. Yeah, 2156. Everything is the same, but this time it's not 1200. We're asking byte address 2156. Which block is this? So first thing we want to do is 2156. What's the block size here? 16 byte. This is the byte address. This is the 16 byte. So it's fine. Calculator, what is this? 134.75. We're gonna round down. So that is 134. So this guy is located 134 blocks. However, we have only 64 blocks. So we need to do 134 mod. We have 64 blocks. 134 divided by 64. I can fit 2. 128. Remainder is what? 6. That means it's a block 6. So next, show the hardware diagram for 8-word direct map cache with a 4-word block. Shader address 0x80000009C, meaning just find the location of this address. How many blocks in this example? What's the size of cache? 8 words. The size of the block, okay? How many blocks? 2. Exactly, 8 divided by 4. So it looks like this, 2 blocks. So index is 0 and 1, that's all. How many bits for offset? So you need to consider block size, not 2. 4. Why? Good. 2 to the m word block. And we say 4-word block. So m has to be 2. And when we calculate the cache size, m plus 2 is the offset. That makes sense. Why? Because this is word, and word. The 4-word block. Each word, we have a 4 bytes. 4 byte, 4 byte, 4 byte, 4 byte, total 16 byte. That's the 4-word block. And if we have a 16 bytes, that means we have a 16 different names using binary numbers. We have to have a 2 to the power of 4 bits to distinguish 16 different bytes. So how many bits for offset? 4. So we need to dedicate this 1100, the lowest 4 bit, as offset. How many bits for index? Only 1, because we can name block 0, block 1. So the index bit is right after offset. And what about the tag? The rest is the tag. Yeah. Index meaning the name for the each block. How many bits do we need to name this guy using the binary numbers? Since we have only 2 blocks, 1 bit, 0 or 1, will do it. So that's why this is the 0 block, this is 1 block. That's why we just need to have only 1 bit for the index. Okay. And our book said this is the diagram. Okay. Something wrong with this diagram. What's wrong? And this is the memory address format. That's what we calculated. Okay. This is the offset, 1100 lower bit. And then this is the index bit. This is tag. So that's why we figured that out. But the diagram is something wrong. What is it? Okay. 2 block and valid bit, tag, and the data, index 0, 1. And the memory address that is 8000009C. This is the tag values 8000, and the last one is 4. And then offset, we don't want to have this line. This offset is all 4 bits. The mux, this is the word addressing. This, when we have only offset for 002 bit, we can get from here, get from here, get from here, get from here. And those are the 32 bits. However, this is the byte addressing, so it should be something like this. We start from 0000, and this last byte is 0011, and 1100, last one is 1111, because we have a 4-bit offset. Good question. So which block? Block 0 or block 1? Block 1, because it's this guy. And then offset as 1100, so it should be right here. This guy. Good question. I forgot to highlight this. Okay. Why offset is the 4-bit? Okay. It's a byte addressing, first of all. Okay. We're going to name all of these bytes. Now, this is one word. This is one word. This is one word, one word. Each word, how many bytes? We have a 4 bytes. 4 byte, 4 byte, 4 bytes, 4 byte. So total 16 bytes. So when we have total number of bytes in a block, if we have a 4 byte in a block, we just need only 2 bits for name them, 0, 1, 1, 0, 1, 1. If we have 8 bytes, we need 3 bits, 0, 0, 0, all the way down to 1, 1, 1. However, if we have 16, we need to have 0, 0, 0, 0, all the way down to 1, 1, 1, 1, which is 15. In order to name all of those 16 bytes, we have to have 4 bits of offset. Yeah, for this guy. This one, right. It should be 1100. Now we have memory address 4, 12, 8, and this is loop. How many times? Again, for 5 times. And it's going to place here, here, and here. So first time when we bring this up, that's the miss, and the rest is going to be, call it, because we have that. So it's this. We good? I don't think so. So we ready? 4. Let's say we have memory address is just an 8-bit. I mean, 8-bit is enough to do all of those. So if it's 8-bit, decimal number 4 into binary number with 8-bit, it's going to be 00000100. And it's a one word. That means 4 bytes. So lower 2-bit has to be offset. And then next 3 bits should be the index. Why 3 bits? Why not 2 bits? Why not 4 bits? Why 3? Exactly. We need to name 8 blocks. How many binary bits is required? 3. 0, 0, 0, all the way down to 1, 1, 1, which is 7. 0 to 7. So that's why 0 to 7. Right? That's the index, 3 bits. Memory 4, that's what we called it. and I need to bring my buddies. Okay? When you bring from main memory to the cache, we have to bring as a block. If this was 2 words, I have to bring additional 4 buddies with me. We need to fill up whole block. We good? Yeah, offset. Okay, that's the size of this block. Size of this block is 1 word. How many bytes? 4 bytes, right? 4 times 8, 32, 4 bytes. If I want to name those 4, I need the 2, right? 2-bit binary numbers. So next, 12. Decimal 12 in binary number is a 00001100. Again, the offset is 0. Okay. So 12 is the first one. And then index value is 011. So should be here. And then value bit now is changed to 1. And the tag, the rest of the numbers, it's going to go there. And 8, we have 00001000. Again, offset is 0. And then the index is 010. And I need to bring my buddy 9, 10, 11 together. So that's that. After this, okay, that's the first 3 times we have a miss because there was no content of the cache. So that was a miss, that was a miss, this is miss, 3 misses. And then after that, 4 is here. Hit, 12, hit, 8, hit. 4 hit, 12 hit, 8 hit. So the miss rate is 3 out of 15. That's how we calculate that. Yeah, give me 2-digit decimal number. 23. Okay, that's a good number. Put this into binary number. 1, 2, 4, 8, 16. So 16, 20, 22, 23. 0, 1, 2, 3, 4, 5, 6, 7, 8 bits. Okay, we good? And then lower 2-bit, this guy is going to be offset. That means this 23 is going to be placed the last. And this is going to be index. That means 101, 110, 111. We're going to put this guy into 101 offset. So this is M23 right there, the last one. Now I need to bring my buddies. Since this is the last one, I need to bring my buddy in here. M22, M21, and M20. So this is the cache content. Did I answer your question? Okay, good, good. Yeah, offset is 10. So 10, so 22. So that is 00010110. So 1 less than that. All right. So if we need to call this guy, and this is our offset, and this is our index, which is the same as this guy. And wait a minute, we had that. So if we call 22 after 23, that's going to be hit. So if we call 22 before 23, 22 is going to be missed, 23 is going to be hit. Exactly, because my location in the 22, it's going to be always here. So when I bring this 22, I bring all of my buddies. Therefore, when I call the 23, it's a hit. It's already there. Yeah. Offset has to do with the size of the data. It is byte address architecture or word address architecture. Now we are all considering the byte address, meaning in here, if we have size as 1 word, how many bytes? 4 bytes. So the offset meaning we need to name this location of this 4 so that I can go grab the right one. So how many bits do we need to name these 4? How many binary bits do we need to name these 4? So if we have a 4, then think about it. If we have a 1 bit, we go 0 and 1. And then I'm out of bits. So if I have, let's say 3 people I want to name as a binary number, then I need to increase this bit so that 1 No, I did increase them. And 1011, I can cover up to 4 people using 2 bits. Right? We need 2 bits. That's the offset. If we have the data size is 2 words, then how many bytes? 8 bytes, right? Now, how many bits we need to name? If we need to name all of those 8 bytes, how many bits of the binary number do you need? If we have a 2 bits, we go 0 all the way down to 11. How many bits to cover all 8? Exactly. Then in this case, we need to have an offset of 3 bits. So we're going to use lower 3 bit as an offset.